everyone, and welcome again to another Friday webinar, an exciting astrophysics webinar. My name is Christian Sasse. I am from iTelescope, and I have the pleasure to introduce our today's speaker, who is Samantha Wong. Samantha is originally from Vancouver. Can you believe it? Our first ever speaker here from Vancouver, and she moved to Montreal to the wonderful McGill University. If you've never seen that university, it's an absolutely lovely campus. And she's there actually doing her PhD program in the high energy, not in the high energy department, but it's in the astrophysics of the high energy. Anyway, Samantha, very welcome, a warm welcome to you. How are you?
I'm good, thank you. Yeah, thanks so much for having me. I'm very excited to be here today.
Very nice. So we're going to go into the very high energy realms of the universe, something that we have very difficult times to replicate on Earth. So this is very, very exciting. So anyway, we all look very much forward to having you here. And thanks for joining us. And it's all to you. And just let me know if there's anything you need, and also with the polls. So it's completely up to you. So go ahead, please, Samantha.
Perfect. So I will just share my screen here. All right, so today I'm going to be telling you all a little bit about what I study, which is high energy astrophysics, and sort of taking you through the different things we see in our universe at some of the highest energies that we can look at the universe with our current telescopes. So a little bit about me to get started. I'm a PhD student at McGill University, which is in Montreal in Canada. So I work with Professor Ken Reagan, and I'm a member of the VERITAS collaboration. So this is a gamma-ray telescope near Tucson, Arizona in the US. I'll be talking a little bit in more detail about this later. I also threw up our website if you're curious. So I work specifically on gamma rays. In just a minute, we'll go through sort of all the different wavelengths of light and why we differentiate between these. So why I say work on gamma rays instead of just, generally astronomy or light. But I wanted to give a bit of insight as to what I do specifically, because a lot of us grad students have very different day-to-day sort of schedules. So I am an observational astronomer, but I work on sort of an older instrument, so all the construction and everything, that's all done. So what I mostly do now is data analysis. So taking observations from the telescope and trying to extract meaningful results from those. And I work on some software development in parallel with that. The software that actually works to take that raw data and turn it into nice images, or kind of as nice as we can go. You'll see some gamma ray images in a second, and they're not maybe quite what you're used to seeing with optical telescopes and whatnot. And I also do observations. So we're sort of an entirely self-contained collaboration. So we maintain the telescope, we go do observations, we analyze our data. So once or twice a year, I fly down to Tucson and actually take observations with a telescope. And we also write our own proposals for what we want to look at. And then I also dabble a little bit in hardware work, but that's not, certainly wouldn't call myself a hardware person. And so today, here's sort of a very brief outline of what we're going to talk about. So I've divided this into 3 sections, and I'm going to pause at the end of each section to take any questions. So I thought I'd give an introduction to just light in general. So what is the electromagnetic spectrum? What sort of stuff are we seeing at high energies? I won't spend too much time on this. I assume maybe other speakers in the past have also talked about this, but feel free to ask any clarifying questions. I'll also be looking at the chat as well if you want to ask questions there. And then I think the bulk of this will be going through our galaxy and beyond our galaxy and looking at what is actually in the high energy sky. What are we seeing with our gamma ray telescopes? And then lastly, I'm going to talk a bit about the instruments that we use to look for at high energies for gamma rays and other sorts of things, and talk a bit about my telescope, the VERITAS telescope. And again, we'll be stopping after each of these, so you won't have to save your questions for too long, hopefully. So just to start off with the introduction, so I'm going to be going through the electromagnetic spectrum and showing you some of the instruments that we use to detect these types of light. So the electromagnetic spectrum just describes light at all wavelengths. So if you remember from, I don't know, high school science, maybe we think of light as both a particle and a wave. And I'm going to be touching on that duality a little bit throughout this talk. But for now, we're going to think of it as a wave. So we start out at longer wavelengths, which mean kind of lower energies. This is like radio waves. So like if you turn on your radio, this is exactly what we have here. But here we're thinking about it in terms of light. So radio waves are really big and they pass through pretty much everything unimpeded. So in particular, we're thinking about our atmosphere. So if they can pass through the atmosphere, we can measure them with telescopes down on Earth. So you can see here, I think this might be a CAD model of the Parkes telescope. I'm not entirely, don't quote me on that, but just sort of a generic radio telescope. And here we have ALMA, which is the millimeter wavelength telescope. And as we kind of move up the spectrum to higher energies, so now we're in the optical wavelength. So I'm sure you're all familiar with the James Webb Space Telescope that just launched a few years ago, the Hubble telescope. We also have ground-based observatories. So optical light as well can make it down to the Earth, although we do get better observations from space. But as we move up from there, so we move into ultraviolet X-rays, this light no longer can make it through our atmosphere. It gets kind of completely absorbed, scattered, all of that. So we need to put our instruments up in space. So typically when we think about high energies, we're thinking about space-based satellite telescopes. But something interesting happens when we get to gamma rays. So this is the Swift telescope, by the way. So that has a UV and an X-ray instrument. As we get up to gamma rays, some of you may be familiar with the Fermi gamma ray telescope that's been in the sky since 2009. And at higher energies than Fermi, what happens is we actually move back down to the ground. And I'll talk about why this is later. But the telescope I work on is actually a ground-based telescope. So there's 4 of these just sitting on the ground so that not in space, we don't have to deal with launching these or any of that. We can kind of move back down to ground-based observations. And then, so when I talk about high energy, we're talking about kind of anything above X-ray, but today I'm going to be focusing mostly on gamma rays. So I'm going to be talking mostly about sort of these higher energies, where the VERITAS telescope is, as well as touching on some of the science that Fermi has done. And then just to give you some sort of sense of how we actually see the universe with these wavelengths. So here we're looking at the galactic plane. So this is the Milky Way galaxy. When I say galactic with that capital G, that's referring to our galaxy, so the Milky Way. So at the bottom here, this is moving from longer wavelengths all the way up to shorter, so low energy to high energy. So you can see radio, and then we move to millimeter, optical, ultraviolet. And as we get up to X-ray, you can kind of see we don't have these nice pictures that we do in optical anymore, these really detailed pictures. And this is when we go back to this duality of light being a particle and a wave, where we're actually detecting very few particles. So when we think of it as a wave, we're just detecting continuous light. And that no longer is the case really when we move up to X-rays. And our ability to reconstruct the positions, so figure out where these particles came from in the sky, is also a little bit worse. We have this lower resolution than you see in these nice optical images. And at the top here is the Fermi gamma ray image of the Milky Way galaxy. And here's another example. So this is our brightest source in gamma rays. We call it the Crab Nebula. So this is a pretty young supernova remnant, among other things. And this was actually seen by humans in the year 1054. And it's kind of one of the brightest and closest things in the high energy sky, as well as across the entire spectrum. So you can see as we move through different wavelengths, it starts to look really, really different. I'll talk a little bit later about why this X-ray image seems to be capturing something entirely different than everything you see here. And then you can see how our gamma ray image is kind of blotchy. And this is what our gamma ray images look like. We don't have really pretty high resolution imaging like you get in visible or infrared. It really is just blotchy, but there's still a lot we can learn from that, even if it's not as pretty to look at. So I work in what we call astroparticle physics. So as we get to really high energy light, we think of light more as a particle. So this is where we kind of move into this photon territory, which is, so one photon is kind of a quantity of light. So like one particle of light. And the reason we call this astroparticle is because we start to use particle physics techniques to look at stuff in space, which is of course the astro part. And because we use particle physics techniques, we tend to use particle physics terminology. So just to give you some insight into some words I might be saying for the rest of the presentation, we think about light as an energy. And we talk about this in terms of electron volts, which you can see at the bottom here is the energy gained by an electron when it's accelerated through an electric potential of 1 volt. If you're not super familiar with that terminology, that's completely fine. It's basically just accelerator language. So when we're thinking about accelerating particles on Earth, we put in a certain amount of energy and we get out a particle of a certain energy. And we think a lot of these systems in space as cosmic accelerators. So this is kind of beyond the energies that we're able to attain on Earth at, say, the Large Hadron Collider, stuff like that. We can actually kind of go to space to study how particles are being accelerated there. And that's one of the goals of gamma ray astrophysics and kind of this broader field of like astroparticle physics. So to put this into context, visible light sits at about 1 electron volt. And here I'm just showing you sort of the entire higher energy spectrum. So this is almost everything sort of excluding radio. And then as we move up, so X-rays are at a keV, which is 1,000 electron volts. Fermi light it's at a GeV, so that's 10 to the 9 or a billion electron volts. And the energies I'm going to be focusing on today, so with my telescope VERITAS, we're actually at a TeV, so that's 10 to the 12, so one with 12 zeros, times the energy of visible light. And then we have this new observatory in China called LASSO that is actually able to go even beyond this to PeV, which is 10 to the 15, which is, the numbers get a little bit harder to actually conceptualize once you, get past here. And so we can actually see more than just light. So in astronomy or in physics, generally, we have this idea of messengers. So you may have heard the term multi-messenger before. And messengers are essentially just different ways of carrying information. You can see this little carrier pigeon. So a way of getting information from a source. So this here is just a cartoon of a supermassive black hole. So you can see, if you've seen any of those beautiful Event Horizon telescope images, you can see there's actually light that comes from material falling into the supermassive black hole. So we do get information from it in the form of light. And that travels all the way to Earth and we're able to study it. But light isn't the only way we can do this. And this is something that we've sort of picked up on and been able to design experiments for in the past decade or two. So this sort of leads me into the first polling question where I'm going to get you guys to try to guess what these messengers are by first figuring out what they're not. So the poll has been opened and I will let you all try to figure out which of the following is not a messenger. So I'll give you about a minute to do so. So I guess as a hint, I've already told you that light is a type of messenger. And I will go into sort of what all of these mean in a little bit. So this is just for fun. Just do your best guess. And I'll give you about a minute to do so.
Very nice. Samantha, just putting things into perspective because it's very difficult to imagine these high energies. If you look at CERN or any of these high particle accelerators and look at the type of energies that they have in collision of particles, how does that compare to the very high energies that you are measuring in with your own with the instrument that you are on, or with even higher energy instruments? Can you?
Yeah, so CERN, the Large Hadron Collider, the LHC, is able, I think the maximum particle it's ever accelerated has been 13 TeV. So this is still crazy. This is super high energy, and we're, with the VERITAS telescope, able to see things up to 30 TeV, so over double that. And we know of gamma rays up to 10 to the 15, so 1,000 times CERN's energy, which had actually come from the Crab Nebula that I showed in all the different wavelengths. That's pretty
1,000
crazy.
times. So that's where that's quite a range. Excellent. Thank
Yeah.
you. Okay.
Yeah. So it gets to the point where we can't build accelerators that are that big on Earth.
Okay. What
All
do you think?
right. Yeah. So I think most of you got the answer right. So we had a few for radio waves. So that was, I tried to trick you a little bit there because I think sometimes we forget that radio is light because we're so used to it being sound. But radio waves are a type of light. So that does count as a messenger. Cosmic rays. So these are really, really fast charged particles. So usually we think of them as like protons or nuclei. If you're kind of thinking about your atom, it's like the middle part of the atom. Dark energy. So most of you voted for dark energy. That's the correct answer. Dark energy is not a messenger. It's this quantity, this sort of unknown quantity that's causing the acceleration of the expansion of the universe. And then a few of you said neutrinos. Neutrinos are also a tricky one. So these are also a type of particle. These are really light particles. They don't interact with much. I put a ghost here because we call them ghost particles because they can essentially kind of walk through walls. So yeah, good job, everyone. So yes, dark energy was the correct answer. And so yeah, the four messengers are just to kind of recap. So light, so this is the entire electromagnetic spectrum from radio through gamma ray. Next, we have gravitational waves. So for those of you who've been keeping up in the past, I guess, 10 years now, the LIGO, Virgo, COGRA, we have all these gravitational wave detectors that have been on and off over the past decade that are actually detecting ripples in space-time itself. So when you have a merger of two, what we call compact objects, so like black holes, just kind of really dense things, they cause the fabric of space-time to just kind of ripple and eventually reach us at Earth, which we can measure and learn more about stuff like black holes that we can't always see directly. I did say that we can see the accretion disk, but sometimes for smaller black holes, that's not the case. Yeah, neutrinos. So these are neutral particles, but they don't really interact with anything, including detectors. They're very hard to detect. We can, because they do occasionally interact with our detectors. A good example of this is IceCube, which is at the South Pole. So you pretty much have to build a huge detector. And kind of the bigger the detector, the more likely something is to interact somewhere. And then finally, cosmic rays, which are, like I said, charged particles, protons, nuclei, sometimes electrons are lumped in there. The definition is a bit loose depending on who you talk to. And these are things that travel at relativistic speed, so almost at the speed of light. And what links these all together is we expect a lot of them to come from the same things in the high energy universe. So here you see a cartoon of, this is a supermassive black hole. So these launch jets of particles out from their poles, which you can see in purple here. And so in green, this is a gamma ray, denoted by the gamma, the Greek gamma symbol. And then a neutrino, which is the new symbol, which is where that's the connection there. So you can see these are both neutral. So they're just going to travel straight from that jet all the way to our telescopes on Earth. But cosmic rays, so it's a little bit small, but this is meant to be the nucleus of an atom, so protons and neutrons. These are charged. So they encounter tons of magnetic fields in both our galaxy and outside of it. So this is like a magnet being pulled by another magnet. They get twisted and bent and get sent off in all sorts of different directions. So we do detect a lot of cosmic rays on Earth. We have the ability to do this, but we can't trace it back into a straight line like we can neutrinos and gamma rays back to their source. So we really have no idea where they come from. And so we need to sort of study these three things together. So gamma rays are good because we know where they come from. They're kind of relatively easy to detect. Neutrinos are harder to detect, but that means they can make it through stuff like this dusty torus around a black hole and give us information from areas where photons aren't going to be able to make it through, but they're harder to detect. And then we just don't know where cosmic rays are coming from. So we'd love to know that, but we can't tell directly. So we need to sort of look at the physics that we learn from studying gamma rays and neutrinos, try to figure out if cosmic rays could be produced in some of these sources. So a little question about cosmic rays. So like I said, we do detect a lot of these things on Earth, even if we don't know where they come from. And we're on Earth, and we sort of act as particle detectors ourselves. So if you think of yourself as an interacting medium, so cosmic ray hits you, and it'll interact with you. They aren't dangerous. You get a lot more radiation from actually eating a banana from the potassium than you do from these cosmic rays passing through you. But so kind of at all energies of cosmic rays, we see they extend up to these PeV, crazy high energies, but there's very few of those. And then as we move to lower energies, we detect a lot more of those. But just in total, how many do you think pass through you every day? So the choices are 100,000, 1, 1,000, or 10 to the minus 2. So this is me trying to say less than 1 a day, so roughly 1 every 100 days. And this is all just approximate. So I'll give you all a minute to put in your best guess.
Yeah, that's going to be an interesting one. We'll see. I'm seeing it evolve, and it's quite diverse. So we'll see. Yeah. So what do you think?
All right, I think you guys are pretty spot on today. So most people said 100,000. That is the correct answer. And then about 10% said 1, 32% said 1,000, and 15% said 1 every 100 days. So yeah, the answer is about 100,000 every day. So we get about 1 every second. Every second, a cosmic ray will pass through us. At lower energies, that can actually be even more. But like I said, these are absolutely not dangerous. So it's something you don't need to worry about. Although if you're an astronaut and you're outside so it's the Earth's atmosphere and magnetic field that largely protect us from a lot of these. So you're not actually being hit by a cosmic ray. You're being hit by, you can see here, the particles it produces when it breaks up in the atmosphere. But if you're an astronaut, it's more likely that you just get hit directly by a cosmic ray. And that is less good for you. So there's a lot of kind of active research going into how we protect astronauts from that. So yeah, I will move on to part 2. I can take any questions in the meantime. I see there's a few in the chat, but if anyone wants to...
Sure. I'll read the first question out for you, Samantha, okay?
Sure.
And then, yeah, we can move on from there. So it's from Tony Smith. Hello, Samantha and everyone. If the early universe was extremely hot and dense, there must have been extreme gamma rays at that time, question mark. Could there have been higher EMR than gamma radiation? And what, in your opinion, on the lack of positrons versus electrons found today, question mark? You may cover this in a lecture, but I thought I would give it a very quick, just come up with it very quickly. Thanks for your lecture, Tony Smith in the UK.
Yeah, so I'll try to cover these one at a time. So when we talk about the early universe, so I will get to this a little bit later, but one thing with gamma rays is they actually get absorbed super easily. So if you're in a really dense environment, you have a gamma ray hit another particle or a bit of dust or something, and it immediately gets absorbed. So it's actually in these dense environments where there might be a lot of kind of short-lived gamma rays, but you don't expect there to be a ton of gamma radiation overall. So like if we had a really hot and dense patch next to our telescope, we probably wouldn't actually be able to see much from it. And so in terms of the lack of positrons versus electrons, so what's interesting at the sort of energies that I work in is we actually see a positron excess in terms of, so electrons and positrons are sort of classified into the cosmic ray domain. So this isn't something I study directly, but it's something I've sort of kept up with. And there's a lot of arguments for this being, is there some sort of source that's just able to generate more positrons through, certain acceleration processes? Is it dark matter? That one always comes up. So we don't really know. I'm not really sure at lower energy is what's going on here, but yeah, I know for us, we definitely see a positron excess and we don't know much about it. Yeah, I think hopefully that answers all of that.
Very good. Do you want to take one more or do you want to move on? I mean, it's all up to you. Do it at the end. What do you think?
I'll save the optical questions for the end. Hopefully I can answer that, I think, in the third section. Um,
Right.
so that's, I think, both of Frank's questions, but those
Okay,
are
cool.
great questions.
Okay.
Um,
You want to say
and
something about Peter? Peter's question? Do you want me to read that one out for you?
yeah, for sure.
Okay, sure. So Peter Lind is saying, Samantha, dark energy hasn't been detected as far as I know. I thought you meant neutrinos. Um, Probably, well, I'm not quite sure what he's referring to here
Yeah, I guess
because,
I'll speak on the first part. So yeah, we haven't detected dark energy. As with everything, there's a lot of theories as to what it was to what it could be, but we really have no idea right now. And yeah, neutrinos are something separate. So we do know what neutrinos are. They're just these very light particles that don't interact very much. Um, but yeah, they're at least right now known to be kind of entirely different things. So dark energy isn't, again, a messenger at all. It's not bringing us any information. It's just something we need to account for what we've observed.
okay, thank you.
All right, so I'll keep it at those two for now, and then we can save some more until the end. All right, so in the next section, I'm going to try to take you through the universe, starting with our Milky Way galaxy, and show you the sorts of things that we can find. Um, so here's the gamma ray sky. So what you're looking at is what we call galactic coordinates, where we show the galactic plane as this flat line. And this is extragalactic space kind of around it. And these are, if you've ever seen these like sky projections before, it's sort of the best way we have of compressing this, the whole sky above us into a map. Um, and the Fermi telescope is in low Earth orbit. It images the sky every day. So we get these lovely all sky images. And at the energies that I work with, yes, is the Fermi satellite. So this is again the Fermi image in the background, and all these points are things we've detected with the types of telescopes that I work with, which are called imaging atmospheric Cherenkov telescopes, or IACTs, which I'll unpack that definition a bit more later. But as you can see, it's these telescopes are on mounts. They're pointing telescopes. It's not quite the same as a satellite where you're just going around the Earth and letting gamma rays hit you. We have about a 3.5-degree field of view for those of you who that means something for. So we have a pretty big view of the sky at any instant, but we are fundamentally pointing telescopes. So we don't necessarily have these all sky images that are from Fermi, but each of these points is a gamma ray source that has been detected by both the VERITAS telescope and others. And for our next polling question, before I actually tell you what these are, I'm going to let you all guess. What is the most common thing, so out of all these dots, that we see at very high energies? So is that stars, active galactic nuclei? So these are supermassive black holes that are kind of actively like feeding on matter from their surroundings. Are they pulsars? These are neutron stars, so the cores of stars after they've exploded at the end of their lives that have really high magnetic fields and are spinning really fast. They're these pretty energetic places, or dark matter, which another thing we don't know what it is. So just put in this cartoon of this dark particle. And yeah, we really don't know what it is, but we know it exists, I guess is my only hint there. So I'll once again give you all a minute to answer that.
In the meantime, I'll bombard a question at you, if that's okay, because it's very interesting when you talk about these high energy telescopes, which I'm sure at least I'm not familiar with, and most of probably the listeners, unless they are specialists in the field, are not familiar with. So coming from the optical field, when you say three degrees field of view, I think we very well understand that's quite a large field, of course. But what is not clear to most of us is, when we take images, we talk about signal, we talk about noise, we talk about resolution, and, all these things we have to do, calibration files and all that. How does that work at these high energies? Is that completely different?
Yeah, so we'll go into a bit about what we're actually imaging later on, but a lot of it is very similar. So our resolution is 0.15 degrees, which is kind of the size of the individual pixels in our camera, which I'll have an image of in the third part. And so our background is actually mostly cosmic rays, because through the technique that we use, cosmic rays and gamma rays actually look very, very similar. So we kind of try our best to separate them, but we have this, what we call irreducible background of cosmic rays. So we get about, I think, 300 cosmic rays every second versus for our brightest sources, about 3 gamma rays a minute. So mostly cosmic rays there. And then because we're optical reflectors, again, in the third part, I'll go into why this is. We have a lot of light from, light pollution, zodiacal light, what we call the night sky background. So we do have to do, flat fielding and a lot of stuff that optical astronomers are familiar with to try to, quantify some of the light that we're seeing. All right. So it looks like almost no one said dark matter. Actually, no one said dark matter. So that's good. That was not the correct answer. And then about 4% said stars. And then it's pretty evenly split between active galactic nuclei and pulsars. But the majority has it. So the correct answer here is active galactic nuclei. So if I go back to this slide, actually, I have a better slide for this here. So here I've labeled what everything in this kind of what we call a sky map, so a map of the sky, everything that's contained here. So active galactic nuclei, AGN, are these red dots. So almost everything we see outside of the galaxy, so everything that's not on this line, is a supermassive black hole, with some exceptions for starburst galaxies and some star-forming regions. Within the galaxy, probably the most popular source are these unidentified sources. They're unidentified for a number of reasons. So you could go as far as saying some of these might be dark matter, and they could be. Other times they're in regions where there's a lot of other stuff going on that we see in other wavelengths. So we can't necessarily pinpoint whether the gamma ray emission is associated with, a star-forming region or a pulsar. We don't really know. Or sometimes there just is nothing there except gamma ray emission. So there's not really a ton of other information that we can use to really pinpoint what exactly is making the gamma rays. We also have supernova remnants. We see a lot of these in gamma rays and binaries. So these are normally a compact object, so a neutron or a black hole orbiting a regular main sequence star. And we see gamma rays from about 6 of those. And then also extragalactically, we have these starburst galaxies, which are galaxies with a lot of active star formation. So that would sort of be, we don't necessarily see a lot of gamma rays at our energies from stars, although we know that the sun produces kind of a lot of lower energy gamma rays. So this is around the mega electron volt MeV scale, which is around 1 million electron volts. So about half of the energy that we see in gamma rays. So I'm going to start out in the Milky Way and sort of explain some of these in a bit more detail and give you some pretty pictures that are not gamma ray pictures, because we've seen that gamma ray pictures are almost always blobs. So here is what I believe to be an artist's impression of the Milky Way. You can see the spiral arms. So we do sit in one of the spiral arms. And then when we look into the center of the galaxy, this is what we see in optical. So this is a galactic center. It's a very bright place. There's a lot going on there. And you can see the galactic plane is very, very bright. And then as you move above it, it really dims out. And then here again is the Fermi image. You can see it maps to that pretty closely. So the first thing that we see are supernova remnants. So this is the Cassiopeia A supernova remnant, which is very young and really pretty in optical wavelengths. And these are, shocks that come out from where the star collapsed. And kind of anytime you have, a shock or an explosion or something like that, you're going to get extreme particle acceleration, and you're going to see things all the way up to gamma rays. And next, so I said I'd come back to this. So we have pulsars and pulsar wind nebula. So I talked about the Crab Nebula earlier. I talked a bit about the supernova remnant. If you're wondering why this is called the Crab, you can look up these like 1800s astronomical sketches that people used to do before you could, do astrophotography like you can today. And they really over-exaggerated these wispy things. They kind of looked like the feet of a crab. But it doesn't really look like that with better imaging. And you can see in the center, there's what we call a pulsar wind nebula, which is the pulsar, the neutron star that's spinning really, really fast, has a lot of energy and is expelling that through winds. And these winds hit the supernova remnant and cause shocks and particle acceleration. And that's what's really lighting up in blue. So this is the X-ray image. In gamma ray, this just is a blob. But this is one of the brightest sort of galactic sources that we see. We can also see pulsations from the pulsar itself. You see kind of a pulse every 30 milliseconds or so. This was, I believe, meant to be animated, but that's okay. So you can see the pulsar here. It has these beams of light, so it's sort of like a lighthouse as it spins around. And every time one of those beams of light kind of intersects our view of it, you get this little pulse. And for this pulsar in the Crab Nebula, we see this across the electromagnetic spectrum. So most pulsars we see in radio, but we also see this one in optical, X-ray, gamma ray, everything. And next we have these binaries and what we call microquasars. So the reason these are really interesting is you can see here there's this kind of big jet that comes off of it, and there's this big accretion disk, and it kind of looks like a supermassive black hole. And it's really a mini version of that. So these are these really active small black holes. So we can't normally see at all if they're just sitting on their own. But when they're accreting matter, kind of just sucking matter off of these companion stars, they really light up and they produce these jets. And it gives us this really close by environment where we can study a supermassive black hole system, but at a slightly smaller scale. So if we're trying to figure out like, how are these jets forming? What's going on in the accretion disk? How is this accelerating particles? We can do that a lot better with these systems that are really close to home. But there's very few of these that we've detected. There's only about 6. But they're very, very cool systems. And then finally, something that's interesting is if we look at the very center of our galaxy, so this is a Fermi image overlaid on an optical image of the Milky Way. And we can see, so what you're looking at here is an excess of gamma rays compared to that kind of gamma ray and cosmic ray background. So just, stuff that's not coming from our source of interest, which in this is the galactic center. And the color scale here is red means brighter and blue is sort of dimmer or cooler. And we see this excess right at the center, and we have no idea what this is. So there's this ongoing debate right now as to whether this is coming from dark matter. So I keep mentioning dark matter, and you might be thinking, how is this related to gamma rays? The idea is that you could have 2 dark matter particles that hit each other, annihilate, and make what we call a standard model particle. So something that is part of the physics we're familiar with. And these could be photons, so it could be light, and we would expect some of these to be at gamma ray energy. So it could be that. Or it could be a lot of these pulsar wind nebula, like in the Crab that I showed before, or similar systems that are just, we can't resolve individually because this area is really busy. There's a lot going on there. You can see it's really, really bright compared to the rest of the galaxy. So it could just be kind of a bunch of jumbled emission from stuff like pulsars that we can't resolve individually. So this is an ongoing debate right now. I think hopefully we'll see this maybe resolved in the next decade or so, but it's something that's definitely interesting. And then outside the Milky Way, as many of you guessed, our most populous source are active galactic nuclei. So what we see from these, mostly we see what we call blazars. So there's all these different names for AGN, which basically just refer to the orientation of this whole system. So a blazar is when you have this jet pointed right at us on Earth. So you basically have a particle acceleration stream right at us. And these are really bright, They're also variable, so we see them get brighter as we think blobs of material from the accretion disk fall into the jet and are accelerated basically along this kind of highway to us. And so these are probably the most well-studied extragalactic source, although there's still a lot we don't understand about them. And next we have these starburst galaxies, where we have a lot of star formation. So they're really, really bright. You can see there's a lot of gas and dust, which typically you'd expect to attenuate gamma rays, but there seems to be a lot of gamma ray production going on in these. So you have a lot of gamma rays still getting out. We don't really know what causes this. We don't know, because in gamma rays, we don't have kind of this really fine spatial resolution that we get in optical. So once again, in gamma rays, this would just be a big blob. So we don't really know where it's coming from. We can't pinpoint to like individual sources within the galaxy. So studying stars in our own galaxy and sort of where their particle acceleration is happening, if we would expect to ever see a gamma ray at TeV energies from a star, stuff like that, helps us sort of understand why we might be seeing gamma rays from these starburst galaxies. And then finally, there is a transient source. So this is something that exists for a short amount of time and then goes away. So it's not something you can study for a long time. So we have gamma ray bursts, which are either from the core collapse supernova at the end of a star's life, so a massive star, or from neutron star mergers. So as I was saying before, we see gravitational wave events when there's two kind of compact objects spiraling around each other, eventually merging. And with black holes, so if you have a black hole merger, you don't expect to see any sort of signal because light just doesn't get out of that. But if you have a neutron star, you get a kilonova. You also might be able to see stuff from neutron star black hole mergers. And these are just kind of huge explosions as these things merge into each other. And actually 2 years ago, we saw what we call the BOAT, so the brightest of all time GRB. And this was actually bright enough that it was kind of disturbing the particles in our own, the ionosphere on Earth. So this was being monitored for, weather reasons, and all these weather observatories were saying, hey, I see this sort of weird disturbance going on. And it was from this, the one that's actually pictured here, this gamma ray burst that happened pretty far away, but it was just, extremely bright. And so I think especially now that James Webb has launched, a question I sort of get often is how far away are the things that you're seeing in gamma rays? So I just said this gamma ray burst was really, really far away. But when I put it into the context of, so James Webb yesterday, or I found the announcement from yesterday, discovered this galaxy at a cosmological redshift of 14. So by kind of my own not very cosmological math, this is about 500 gigalight years away. But so this bright GRB that we saw, which the brighter something is, the more photons are going to make it to Earth without being absorbed, was only at about a redshift of 1. So this is how much the universe has expanded since those photons left the source. And the reason for this, so if you look at this graphic on the right, if you have, so we're going to go back to thinking about light as a wavelength. So I said earlier, these radio wavelengths have a really easy time making it to Earth. So they're kind of like a big cruise ship moving through waves. They're not really going to notice even kind of medium-sized big waves in the ocean, just because it's kind of so big. But if you're in a kayak, even small waves, you're going to notice a lot. And if you're kind of in a big wave, there's a big chance, it might like totally, wash over you. So it's the same with light. So radio waves, even through optical, even X-ray, to us at least, are able to make it pretty far through the gas and the dust of our universe. But gamma rays don't. They're very short wavelength. They get very easily absorbed by gas and dust. So we actually can't see them out super far. Most of the stuff is very, very close to us. Most of the things we see are in our own galaxy for that reason. And of course, there's a lot of things that are beyond our current knowledge of at least the universe or how these systems work that we're looking for. So stuff like dark matter, counterparts to fast radio bursts, which are these things that we only see in radio, transient events. does light travel faster than the speed of light? Is there new physics that can do that? Is something we're looking for. Understanding the gamma ray background that we just kind of see around us. Were there black holes in the early universe that evaporated, and stuff like that? So I will take maybe a couple questions. I think I might be running a bit short on time from that section.
That's okay, Samantha. Any preference on if you're just having a quick look through the questions?
Yeah, I don't see any that are super new. I can maybe save some of these till the end.
Okay, that's fine. That's fine. Yes.
All right, so now I'm gonna get into how we actually detect these gamma rays and how my telescope works. So we use something called the imaging atmospheric Trenkov technique, which is something I think I've said a couple times but haven't gotten into. And this takes advantage of the fact that the Earth's atmosphere is opaque. So we might think that, okay, this blocks out all of this high energy light. How are you looking at this on the ground? I'll see if my little animation works. So you have your source here. This is a cartoon of a pulsar wind nebula, and you have your photons. Little cartoon photon coming down, traveling through the universe. Everything's okay as long as he doesn't get absorbed by anything else, but he's probably fine if he's not coming from too far. But as soon as he gets the atmosphere, you don't have a gamma ray anymore. So our atmosphere breaks apart these high energy particles. And what happens to them is, so the particle hits an atmospheric nucleus or just any particle in the atmosphere, and it's gonna what we call pair produce. So that means it makes an electron and a positron, which are represented by these branches here, which are also pretty high energy. So through different radiation processes, those can continue to make photons, which continue to make electron positrons, and you get what we call an air shower. So it's a shower of particles. And I've drawn this sort of cone of blue around it. And the reason for that is if these particles, so the electrons and the positrons, if they can travel faster than the speed of light in the atmosphere, which you may be saying, well, nothing can travel faster than the speed of light. And that only applies to vacuum. So that applies to space, but not whenever you're in a medium. So if you're in air or water, you can end up in these situations where you have energetic particles traveling faster than the speed of light. And this creates sort of the equivalent of a sonic boom. So, for planes traveling faster than the speed of sound, you get an audible sonic boom. And for light, when this happens, we get this visible, so this is in our visible light spectrum. This happens very quickly, so we can't see it, but if you were to slow it down, we may be able to see this with our own eyes. It's just this blue optical light that comes down in a cone and then sort of hits the atmosphere as a pancake. And I do have a video of this that I will try to show you. Hopefully the quality isn't too bad. So you can see this red is branching out. So each of these are individual particles falling down, and they're developing this blue light, and which pancakes down onto the Earth in this kind of big circle that we call a light pool. And this is a model of Arizona. You can see from the Google Maps where my telescope is. And it's this blue light that we're actually imaging with our telescopes, which is why I've said that they are kind of fundamentally optical telescopes. So to show you sort of what our data looks like, so you have this light pool coming down, and it's about 100 meters in diameter. So, all of our telescopes can comfortably fit within that light pool. And you're sort of looking, so it was hard to do in cartoon version, but you can imagine the telescopes are looking up at this black axis here, which you can trace right back up to, your original black hole or pulsar, whatever your source is. And kind of when you're looking to the side like that, what you end up seeing is an oval. So on the right here, so this is a gamma ray that's a little under 2 TeV. And you can see each telescope kind of, I'll try to trace them out for you, captures this oval shape. And the reason for having more than one telescope, so what you may have thought, what I originally thought is this might be interferometry, sort of what we do in radio, where we can make our telescope seem bigger by having more of them. That's not quite the case. What we do is you can see that each ellipse looks different in each of these photos of the exact same, what we call a shower. So this blue light. And because each telescope is in a different position on the ground, you can find the point where all of these intersect. So these aren't, I've just kind of plotted this in a grid, so it doesn't actually correspond to where the telescopes are. But if you trace each kind of ellipse axis and find where they intersect, that'll tell you where your gamma ray actually came from, because you're, looking up at it with each telescope. So it's a bit of geometry that you have to do in your brain there. But that's the reason for having 4. If you just had 1, it would be a lot harder to tell, especially because you can't tell, if it came from this way or if it came from this way. If your ellipse is less elliptical, it also makes it a little bit harder if it's more circular. And this also helps us tell the difference between gamma rays and cosmic rays. So gamma rays make these nice ellipses. Cosmic rays produce a lot of other particles besides electrons and positrons in our atmosphere. So they end up in these like really kind of laterally large and blotchy showers, because these particles don't make kind of these clean, nice tracks downwards that go out to the side and all of that. So you kind of end up with this huge blotch instead of a nice ellipse, which is how we at least try to tell the difference between gamma rays and our background, which is cosmic rays. So here's sort of what the array of telescopes looks like. So you can see there's 1, 2, 3, 4, and there's actually a 5th telescope on site, which is a prototype for the next generation of gamma ray telescopes that we have, which is pretty exciting. And so yeah, this is near Tucson, Arizona. And you can see that these are all just regular mirrors. So they're in facets because this is 12 meters across. It's difficult enough to make, big mirrors for optical telescopes that are only a few meters. I think with the really large optical telescopes that have been proposed, that's definitely a challenge to get a mirror that's good enough for that. But because we're imaging something that's actually so big, so we're not looking at a small point in the sky, we're looking at the shower, which is 100 meters in diameter. So we don't need to have this really great mirror resolution, which is why they're done in facets. And then they all focus to the camera. So to compare this to a telescope that you all might be more familiar with, so just kind of a standard optical telescope. So the optical reflectors, which in most of these, I forget the name for the design, you all probably know this better than me, but just for your kind of standard reflecting telescope, you have 2 mirrors. Here we only have 1. We're just directly focusing all of the blue triangle of light that we see into the camera here. And yeah, so this is 12 meters across. They're very, very large. There is not much I can show you for scale. These are kind of like the little parking things in parking lots, like stop you from driving through stuff. This is kind of a small trailer where our electronics are. And then a camera. So, you might be used to like seeing a CCD camera that you can attach onto your eyepiece. This is our camera here. What it actually looks like is it's this array of 499. That number comes from just arranging this in the circular pattern. And these are photomultiplier tubes. So these are usually used for particle physics. They're these really fast responding, they can see dim light. It's just kind of a different type of pixel than like a CCD that optical astronomers may be more familiar with. And then finally, so this big thing down here is what we call a pedestal. So this is basically just an alt-as positioner that moves our telescope around in the sky. And this whole thing, we can move at about 1 degree every second. So they actually move pretty fast despite how big they are. And there's currently 4 of these sort of majorly operating telescopes in the world. There's a bunch of ones that are, kind of coming online or are prototypes like the one I showed you before. But there's 3 in the Northern Hemisphere. So this LST is also a prototype for the next generation of telescope, but it's fully operational, it's taking data. So these 2 are both in La Palma in the Canary Islands. We're in the southern US. And then our only Southern Hemisphere instrument is HESS, which is in Namibia. And you can see here, so here's that Fermi image again with the galactic plane. And so this is the Northern Hemisphere. Because everything's been, transposed to these galactic coordinates, you end up with this kind of weird Northern Hemisphere, Southern Hemisphere divide. And then this here is the South Pole. And then we have a similar one that I've accidentally blocked out here for the North Pole, where it's just really hard to actually see down there. And then other examples of gamma ray telescopes generally is we have the Fermi Large Area Telescope, Fermi LAT, which I've talked about a bit already. I briefly mentioned this. So there's also these water Cherenkov detectors that directly detect the particles from that shower. So they're not imaging the light in the atmosphere. They actually have kind of their own detector where the particle goes in and creates a little burst of Cherenkov light. And there's a camera at each of these. So these are all filled with water. These are probably the size of like a shed or a small building. In Mexico, this is called Hawk. And then LASSO in China is like an even bigger version of this. So inside this building here is a bunch of these, and then around are just little blocks of scintillator, which kind of produce light when a particle interacts with them. And this is a kilometer squared. So this is really, really huge. And then, so this is the next generation telescope I keep talking about, which is the CTA telescope. So these kind of medium telescopes here are about the size of VERITAS. These large ones are, I think, over 20 meters across. There's 4 of them. And then I think I've cropped it out just slightly. There's a bunch of really small telescopes. So this helps us image gamma rays at kind of even lower and even higher energies than VERITAS. And there's even more of them. So when we're trying to talk about like getting direction by intersecting each of those ellipses, there's a lot more of those ellipses to intersect. So we get a lot better angular resolution with these ones. And I thought I'd also share a bit about what it's like to actually observe with VERITAS, because this is something that I'm really fortunate to actually get to be able to do kind of whenever I want to. We're always actually looking for observers. So it's more of a question of how often I want to go to Tucson. So here's one of our control computers. I can see we kind of monitor, these are just the currents in all of our pixels, just making sure everything's okay. Here's our actual data coming in, and I intentionally zoomed out a bit because I don't want to give away too much private information, but each of these splotches is a gamma ray. These are our gamma ray rates. This is, our tracking software. We're right beside a ranch, so here's a whole lineup of cows outside the telescope. So we are just kind of in the middle of the desert in Arizona. And our telescopes are outside, so we do a walk around at the beginning of each shift. We have a checklist of, electronics and stuff that we check. And luckily, we're not a radio observatory, so we can use walkie-talkies to talk to each other. Here's me, and this is the back of the camera. So this is the wires coming out from all the pixels. There's a lot of, the electronics are pretty heavy for telescopes. And here's me next to one of our telescopes. So you can kind of, I'm actually standing up on a hill here. So you can see the scale here is just enormous. And here at the end of the night, so our telescopes are at the bottom of the mountain, but we're part of the Fred Lawrence Whipple Observatory, which also has a bunch of optical telescopes that are part of it at the top of this mountain. So you drive up this windy road after your, 12-hour shift, which it's gorgeous up there. It's really, really beautiful, but it's a very long drive when you're tired. So I will stop there, and I'm going to take any questions. So I was recruited for this talk today because I'm an AstroBytes author, where I sort of break down high energy papers at a more accessible level. You can also check out my website if you're interested, which I will admit is not very good, but at some point I will put effort into improving that. So I'll take questions now.
Well, many thanks for that, Samantha. It was an absolutely magnificent, very, very inspiring talk. I was fascinated also by the photomultipliers that you use. I didn't know that. You have 499 photomultipliers, and I worked with them, so I can imagine the wiring must be insane there.
Yeah.
It's crazy. So thanks for that. Just a quick question from me, and then I'll hand it over. Can you tell us a little bit more about the thesis? I mean, you've given such a wide background, but what is the particular area that you're actually working on? Is it data science? Because you're mentioning all these different areas. What is it that you're focusing on in your thesis?
Yeah, so I work mostly on pulsars. And so I think I said I was going to touch on this, I never did. So how the optical system comes into it. So by default, we're a gamma ray telescope, but because we look at optical light, we can also get what we call a time series. So kind of how bright the optical light is as a function of time for things that we're pointing at. So we can also get optical information about these things. And for pulsars, you do see these blips. So we can't do any imaging, but anything that's changing in time, you get information about. So I'm working on maybe detecting some new pulsars and optical wavelengths where current instrumentation really isn't able to do so. But because of kind of the way our gamma ray telescope works, we might be one of the most sensitive telescopes in the world to these things. So I'm looking at discovering some of those. And then at the same time, we get free gamma ray observations on the pulsars and their environments. So both detecting new pulsars that pulse in gamma rays, because we only have 3 of those, and looking at these nebula around the pulsars and understanding those. And I mentioned some of these unknown sources that are in these confusing regions. So trying to pinpoint those to pulsars to see if they're, if we can call them pulsar when nebula, or if there's something separate that just has a pulsar nearby. So that's sort of the focus of my PhD research.
Very, very interesting. Do you mind just stop sharing, then we can see you better? By the way, there are a lot
Yes.
of praises coming in about your excellent talk. So thanks everyone for attending. So I'll go through it now. I think the first question from Frank Kenny, you have addressed a lot of this already. So the VERITAS website says the telescope is an array of four. Yeah, that's what you said already. In the giga to tera electron volt. Can you speak for the optical gamma dual configuration? I think you did answer that very well, because you said it's not interferometer. You explained that really well. It's more for type of triangulation. You understand where it comes from, right? So is there anything you
Yeah,
want
I
to
will
add,
say.
or
Yeah, so in terms of the optical work, so yeah, I'm working on sort of a pilot project for these pulsars, but other things that we do is we look for asteroid occultations. So when an asteroid passes in front of a star, you see that star dim, and you can actually get information about the star from that and the asteroid. So the radius of the star, the shape of the asteroids. That's a very successful optical program we have. And we also look for optical counterparts of fast radio bursts, which I kind of briefly touched on. So gamma ray and optical counterparts. Those are 2 things we can do. And we're going to do an entire kind of overhaul of our optical backend in the next year. So hopefully we'll have some pretty cool science results coming out soon.
excellent. I love that you said it. They're looking for observers. It's more when do I want to go? That's quite a twist. I haven't heard that one before. So anyway, Frank's second part here. Is any optical work performed with this configuration?
Yeah, so like I said, yeah, I'm trying to do the pulsar stuff, and then we have the asteroids, fast radio bursts, and we're always looking for more optical things to look at. But yeah, because we're not able to really do imaging with this, so yeah, like I said, our angular resolution isn't great because we're optically trying to just look at this huge pool of blue light. So we're not necessarily optimized to look at like detail within a galaxy or something. But anything that's quickly varying, we've thought about doing if we're not doing already. And we haven't, I think we put out a paper on our asteroid stuff, but hopefully there's much more to come in the next couple of years.
Very good. And John is asking about AR3664. So that's a solar flare that we've just observed. It's back again. So he's probably his questions relating to the energy there as compared to the energies you're working with.
Yeah, so it's a little bit lower. So we actually don't worry about solar flares too much. It actually, we kind of just missed that. It also interferes with the cosmic rays, the solar cycle. When it's at a high, it attenuates cosmic rays because of magnetic fields and stuff like that. It's not super simple, but it's kind of just below the energies we worry about and that Fermi worries about. This is more MEV sort of stuff. But we might expect to see, so from these M dwarf stars that are quite small, but they're very, very active, they might actually be energetic enough to produce solar flares that potentially could be detectable at gamma ray energies, but we haven't really seen any of that yet. But generally, yeah, we don't actually worry about the sun very much at all. Although, because we are an optical detector, one thing that actually happened recently when we had the aurora come down really, really far south, the observers noticed that it was really, really bright in the camera. And they went outside and actually saw the aurora, which is not something you usually worry about in Arizona.
Interesting. Right.
Yes, but it does. So that's sort of a really indirect way that the sun does affect us.
Very good. Thank you. And Derek is asking about the Large Hadron Collider interfere. Can that interfere with your gamma ray telescope?
Yeah, so we're very far away from the LHC for one, but also, so the particles in the LHC are very well contained within it. And they're, it's a hadron collider, so they're colliding the particles and looking for the energy for that. And to get sort of the optimal results, you want that to actually happen in your detector. So you actually don't want too much energy to escape. So even if we were, in the same country, continent, it still wouldn't have a huge effect on us. So yeah, it's actually pretty well contained, which is, good for us generally. You don't want a proton beam going through your town, but yeah, so it's not something we have to worry about at all. It's mostly just optical light, honestly.
And Tony, I see you put, that's great. You put a lot of questions, but I'm only going to take one question here from you because I have to give the others also a chance. So Tony's says one more. What is your opinion of MON proposal by Milgram?
Yeah, so this is not, I don't want to speak too much on this because it's quite far outside of my field. So yeah, this just has to do with kind of the formation of structure in our universe, which is kind of much larger scale than what I usually think about. I think from what I've seen, just, structure formation from like smaller things to, growing up to galaxies and galaxy clusters and whatnot. I think most of those arguments make sense, but I know, we're always trying to look for, proof of things or proof that we can reject something. So I think it definitely is something that's still somewhat of an open question.
Right. And then we jump to Natalia. Natalia says, thank you very much for the great lecture. I agree. I wonder what comes to us first in the case of neutron stars merger, gamma rays, optical rays, neutrinos, or gravitational waves? And a similar question about massive star explosions. What will we register first?
Yeah, that's actually a really great question because I think one thing that is impacted by that is actually our observation strategy. So who sees this first and then tells everyone else to look at it? So one thing I will say about kind of light of all types is it does get absorbed, or sometimes in these mergers or explosions, you have this really dusty environment where stuff does get absorbed and has a hard time getting out. So usually we see light last. So gravitational waves are completely, unimpeded as they travel through space and time. So we definitely expect to see those first, with neutrinos as a very close second. So for supernova, which is one of the sources that we have kind of a confirmed neutrino detection of, I didn't go too much into this, but we, because our ability to detect neutrinos is, somewhat hindered by the fact that they're hard to detect, we're not sure if they come from supermassive black holes. We think they might. We're not really sure what they come from. So they're hard to associate with a lot of events, but we have seen them from a supernova, supernova 1987A. And they're one of the first things to come out because while there's this really dusty environment that's stopping all of the, optical, gamma ray, all of this light, the neutrinos just stream out. So if it's, close by and there's a lot of them, coming towards us, we're able to detect those pretty early on. And we're also able to detect gravitational waves really early on. So what we do is we, get an alert from LIGO saying there was a gravitational wave merger over here. This looks like something that has a neutron star, so we'd expect some light from it. And then we go and follow it up. And usually the light lasts a bit longer with longer wavelength light, actually usually coming later because sometimes you'll have like light reflecting back and forth and it gets, if it was originally a gamma ray, it gets scattered down to a lower energy and then, bounces around and eventually comes to us. So light can actually take quite a while.
Wow, how interesting. Thank you. A very good question that was. Peter, is it similar to the Compton scattering effects in the atmosphere, but on the gamma wavelength spectra?
Yes, I'm not sure exactly what this is referring to, but I'll try my best. So Compton scattering is generally when you have a photon hitting an electron, and it can kind of either bump up the electron energy, or if energy is lost in the collision, it can go down to lower energy. And in gamma rays, we actually think of what we call inverse Compton, where you have an electron or some particle hitting a gamma ray photon and bumping it up to a higher energy. And of course, it can go to a lower energy as well, but we're interested in the ones that get bumped up. So you could have something that's originally an X-ray, and it gets bumped up to a gamma ray. But if we think about the entire electromagnetic spectrum, A lot of these different wavelengths are actually coming from the same places. It's just some of them are being scattered up to gamma ray energies.
Yes, I think that's what he means, because I'm just looking further down. He says Compton scattering is about photons, but what you described is about gamma rays. That's what he's saying. Yes, so
yeah, so gamma rays are photons as well.
yes,
So yeah, there's a lot of kind of interchangeable language about light
yes,
here.
yes.
But yeah, so gamma rays are light, which are photons. So this is all
Right.
the same stuff.
Very good. Raymond is asking, how do you determine the energy of the detected gamma rays?
Yeah, so that's actually a great question. So that actually has to do with, if you remember when I showed those ellipses of what our actual data looks like, so the size of that ellipse is determined by how bright the shower is. So if you have a shower that's really dim, you kind of don't get that many pixels lighting up, but if you have something really bright, then you get kind of this huge ellipse in your camera. And the brightness is determined by the particle energy. So we do simulations. So basically we make all these fake gamma rays and we throw them at our detector and see what they look like. And then we know the true energy of that simulated gamma ray and we know what it looks like in our detector. So then we can say, okay, for this energy of gamma ray, we expect to see this. And then we kind of make a big table with all of those values. So like the size of the image compared to the original gamma ray. And of course, there's a bit of error on that, but we can, reconstruct that reasonably well to about 10% of the true energy. But it's definitely not something that's easy to do.
That's a great question. Good. Okay, Hans, what is the time resolution of the optical system? How accurate can you measure the TOA of the photons? Time of
Yeah, that's also a really good question.
Mhm.
I'll start out by saying that, so one of the reasons that we're kind of so optimized to do this rapid optical stuff is because these gamma ray showers happen on like nanosecond timescales, like these big pancakes of blue light falling down. So our PMTs, our photomultiplier tubes, are responsive at nanosecond timescales. Our optical backend is kind of really the bottleneck here. So this is just kind of a what we call a pathfinder device. So something just to test if this is going to work. And that right now is sensitive at about kilohertz. So it can detect, it samples around 1,000 times per second. And eventually we're going to integrate that into our whole gamma ray system. So we will have that true nanosecond sampling for optical, which is going to be pretty crazy.
Wow, really interesting. Thanks for that question. Great question. Okay, Peter has another question. Oh no, wait, we had that. Sorry, let me just Tony. Okay, Tony, I'll take one. I'm recording. Okay, it's recording. Wait a minute. Let me just get I got missed something. Kevin, sorry, let me just do this. What is the coating of your parabolic mirrors? Are the cells glass or some other type of material?
That's something I don't know off the top of my head. It's some aluminum sort
Right.
of coating. I'm not entirely sure. But yeah, they do need to be recoated quite often because we're in the desert, so you do get a bit sandblasted.
Yeah, so it would probably have some glass coating, otherwise it would be so quickly ruined, right? I mean, that's my guess. I don't know, but interesting. Okay. Okay, one final question from Peter. Yeah, so it's about energy levels. The photons jump to other energy levels. Um, yeah, I think that's what you were talking about. So anyway,
Yeah, so this isn't quite the same as like when you think of an energy level in an atom where you have an electron at a certain state. It's just the energy of the photon itself. So photons are kind of weird to think about because they are particles, but they're, they don't have a mass. They're kind of these weird things. But it's just the energy that the photon itself kind of has, which, yeah, it's not super easy to think about that. But yeah, I think basically, I guess you can think of it as, you go from this radio thing, this radio wavelength or radio photon where the wavelength is super long, it doesn't have a lot of energy. And then you compress that wavelength kind of as you get to higher energies. And you can get up to gamma rays, but it's fundamentally the same the same thing. Like you don't necessarily have an electron jumping around because there is no electron because it's not an atom, but it's just kind of the intrinsic energy of the photon.
Very good. So that leads us to the end of today's presentation. Thank you very much to everyone for all your great questions. And of course, especially a big thanks to our guest, Samantha. That was absolutely brilliant, magnificent. So we wish you all the best. And we hope you get your PhD in whatever it is, 2 or 3 years. And then it'll be interesting to see how your life continues. So please do stay in touch. Thank you to everyone and have a wonderful weekend. Thank you.
Yeah, thank you, everyone.